Okay, stats. Let's talk about different ways this kind of problem in 10.2 can be worded. When it asks for something unusual or unlikely, that's when they're statistically significant. Now remember, we talked about this earlier when something was roughly more or less than 2 standard deviations away from normal. We said it was unusual. That's the same as statistically significant and unusual. They're kind of similar. So this is the flip side of the confidence interval. Whereas the confidence interval likes to catch, say, the inner 95%, the unusual stuff is when it's the outer 5%, which is the 2.5% on either side. So a researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving. So p hat is 534 over 1,000. Does this suggest more than 50% of people favor the policy? Or is it possible the true proportion of registered voters who favor the policy is some proportion less than 0.5 and we just happen to survey a majority in favor? In other words, would it be unusual to obtain a sample proportion of 0.534 or higher from a population whose proportion is just 0.5? What is convincing or statistically significant evidence? What does it look like mathematically? Well, first let's build the probability model. Make sure p hat is normal. So multiply n times p times 1 minus p. So in this case, if we assume it's 0.5, that's our null. So our null is p is 0.5, so we're expecting for the average from the population should be the same because that's how that works. So is 1,000 times 0.5, and of course 1 minus 0.5 is the other 0.5, greater than or equal to 10. Yes, because it's 250, and that is definitely greater than or equal to 10. Now, the standard deviation of the sampling distribution is the square root of p times 1 minus p over n. So let's take the square root of 0.5 times 0.5 over 1,000 and put it in the calculator. Looks like we get approximately 0.016. Let's draw a picture. Now what they want to know is here's 0.5. Somewhere over here is 0.534. Now if I make a critical region of 2 standard deviations, where does the 0.534 fall? Does it fall in the shaded region or not? So let's do the classical approach to see what the z value is. So our value from our results was 0.534 minus 0.5, and we just did the standard deviation up here of 0.016, and when we do this, we get 2.13 as a z-score. Now 2.13, is that more than 2 standard deviations away on either side? Yes. So do we reject the null? Yes. There is sufficient evidence to conclude that the proportion is likely larger than 50% in the population. Proportion is greater than 0.5. This is another way this type of problem can be worded to get you to draw a conclusion, or another use for this type of classical approach. Now, what about the p-value approach, the second type of approach? So the p-value approach, instead of comparing our critical values, we'll compare areas. So basically, we talk about the 5%, the outside 5% being the unusual terms. So what they're going to do is they're going to find the value specific area based on its z-score using our z-table, for example. Say, is that a less than 5%? Is that a more than 5%? Or if the alpha is 10%, you're comparing it to 10%. So high p-values close to 1 means it's likely you will not reject the null hypothesis. Low rare values for a p area, like 0.0001, you're going to be like, okay, reject that thing. So from our same example, how likely is it to obtain a sample proportion of 0.534 when the population whose proportion is 0.5? So we got that z-score of 2.15. Now we go to our z-table. What's the probability that z is greater than 2.15? Remember, to do to the right, we have to do 1 minus. So we found the z-score for 2.15. It's 0.9842. 1 minus that is 0.0158. Now, 0.0158, that is our p-value. That means there's only a 1.58% chance of getting a z-score of 2.15 or greater. That's pretty unusual. 1.5 to 2, really 2 samples in 100 at most will give the sample proportion. Because this is unusual, we would say this is evidence against the null hypothesis. So let's just start out a little slow. Just by finding the p-value before we do a whole problem. Determine the critical value for a left-tailed test regarding the population proportion at the alpha 0.01 significance level. Okay. So we are looking for a left-tailed test regarding a population proportion at a 0.01 significance level. So 0.01, this is the area or p-value. So for it's a left-tailed test, we're looking for the critical value where we see 0.01 is to the left of the z-value. Now in that table, that's negative 2.33. So in order for this to work from a classical approach, we would need, so for classical approach, we're looking for a z-value that's less than the negative 2.33, right, in order to reject. Now for the p-value approach, what we're really looking at is we're taking our critical values, taking our z-score and looking at the area to the left, and we're looking for a p-value that's less than our more rare than a 1% chance in order to reject. Now in the next video, we will actually do an example of this problem and do a p-value example as well.